All right, guys, I want to make a quick video about the second derivative test. It can be a very handy test to determine maxes and minimums. So yesterday, we talked about how the second derivative can tell you information about the concavity of the original function f. And we've also talked about how the first derivative can determine the potential maxes and mins. But then you'd have to do some further investigation to determine if it's a max or min by looking at the signs and sign changes, and also if it's a plateau. So let me tell you basically how it works. So let's start with a function that is pretty familiar. So let's just pick a parabola. And before we even start this question, we know that this is a positive or a concave up parabola because the leading coefficient's positive. And so if I asked you if this parabola has a max or a min, you should all say minimum, just because you know what the graph looks like. But if we used calculus, the idea is that the derivative is 2x plus 2, and if you set the derivative equal to 0, you get x equals -1. And from our lessons, if we knew nothing about the graph, we know that this is a potential max or min, or neither, and you'd have to do something else. So let's say we don't know how to graph, but what is the second derivative test? So the second derivative test with this example says that if you take the second derivative of this same function up here, it would be 2. And in words, the second derivative test says that if you take the point, which we call a critical value, any value that the derivative is equal to 0 or undefined is a critical value. And those critical values could be one of these things. So if you evaluate the second derivative with the critical value found in the first derivative and look at the sign of that, now this one's kind of goofy because the second derivative is always 2, right? It's a constant function. But really, that 2 is greater than 0. And so in words, what that means is at this potential minimum, this x value, we determine that the concavity is positive. And so what am I trying to say? If you have a point that's a max or a min, but you determine at that point that it's concave up, in this case, it's concave up because it's positive. So this is in the ballpark of that max or min, and it's concave up there. Using those two facts together, this has to be a minimum because the concavity there is positive. Let's do it with one that's a little less familiar. So let me see if I can scroll. Oh, it's kind of fun. All right, here's a cubic function. Here we go. Let's just bust out some quick derivatives. So f prime of x is going to be x squared plus 2x minus 15. And if we set the derivative equal to 0, what adds to 2 multiplies to 15. So we got something like this. We get the critical points of -5 and 3. And remember, summarizing what we've learned so far, these are potential maxes and mins. So let's assume, again, that we know nothing about the graph of this. The idea is we're going to take the second derivative. In this case, it's 2x plus 2. But now, if you think about, well, when is the second derivative positive? When is the second derivative negative? When is the second derivative 0? It depends on what x is. So maybe we'll come back to that in a second, but let me finish my thought. The second derivative test says, if I evaluate the second derivative with one of these critical values, this would end up being 2 times the quantity plus 2. I'm taking this right here, plug in -5, and I get -8. This says that f is concave down at x equals -5. Now, I know this is a max or a min, but if it's concave down, just like that, then it has to be a max because of this picture. It's like if I draw it harder, it makes more sense. I'm going crazy. All right, so max at x equals -5. Similarly, the second derivative test says if I substitute in the other critical value, 2 times 3 plus 2, I get +8. Well, that means it's concave up at that critical point. So it must have a minimum there. A lot of students like this. I like this just because I don't have to check signs. You know, the other way is to look at the behavior around -5. Like check -6, check -5, check -4. Does it actually change concavity? You know, is there a minimum there? A couple other things just to kind of recap the lesson so far. If you set this equal to 0 and solve, what is that going to give you? Pop quiz. I'll give you 3 seconds to think about it. If you need more, pause the video. Now, if you set it equal to 0 and solve, you get -1. And remember, that value is a point of inflection as long as the concavity changes. But based on what I did over here, it looks like the concavity changes because it changes signs. And then for all my visual learners, I would lump myself into that group. We know that a cubic with a positive coefficient kind of has this shape, you know, like that. And if you just think about the behavior here, this would be where a maximum is. This would be where a minimum is. And then somewhere in here is what I defined as the point of inflection. But look at these interesting values we found. According to my work, it's beautiful, this -5 was a maximum. I'm trying to find it on here. There we go. 3, again, not drawn to scale, was a minimum. And this last thing I found, -1, right, somewhere in here, was our point of inflection. So always ask yourself, does this make sense? And this way we kind of backed it up visually, and this is a great demonstration of what we call the second derivative test. Thank you for tuning in.